Hey, future doctors. Thanks for tuning in to Spoonful of Sugar, a podcast made for medical students by medical students to help the medicine go down. My name is Akiva Eleff, and I am a third-year student at Ohio University, and I will be your host today. This is the final part of the series on stats for COMLEX and USMLE. In this finale, we will look at measures of central tendency and statistical methods to provide value to research and analysis. What we're going to discuss in today's episode more generally is practical applications as well as the finishing touches to what you need for boards. So if you're going to listen to anything, if you're interested in assisting on any research project, what we discuss here today is going to be things that can really give you a leg up. So let's jump straight into stats. So we have a better understanding of study designs, initial interpretation with our contingency tables, as well as the basic equations that we have talked about. And we can now evaluate how are we going to use all of this and how are we going to understand all these results. In other words, how are we going to interpret and publish our findings? So let's start off with some more terms. And the first term we're going to talk about, and I'm sure a lot of these terms, if you've taken a college stats class, are going to be repetitive, but for completeness sake, let's start off by talking about the bell curve. So what is a bell curve? A bell curve is defined as a measure of central tendency in a normal distribution. So in perfect conditions, you're going to have a relationship between mean, mode, and median, which is all equal, right? So mean will equal mode will equal median. This is greatly affected by skew, which is caused by outliers, either greater or lesser than the 50th percentile, causing positive or negative, right or left skew, respectively. Positive skew means a right tail, which means mean is going to be greater or less than median. It'll be greater. And then median will be greater or less than mode. It'll be greater as well. So in order, it's mean, median, mode. And then we have negative skew, or left tail, which is the reverse of this. So therefore, mode is going to be greater than median. Median is going to be greater than mean. Great. Now that we talked about these terms, let's just run through them. What do they mean? What is the mean? Yep, the mean is the average. So this is affected by outliers or not affected by outliers. It is very affected by outliers because these are and the equation for this is the values of interest divided by the total. That is the average. Median is the middle value, median middle, when sorted from least to greatest. Is it affected by outliers, yes or no? No, so median is not affected by outliers. This is actually a very useful piece of information to hold on to for some kind of more niche statistical analysis. For example, if you wanted to know where you fell, maybe in your med school class, if you had class rankings at your school, then a median might be more helpful than an average because it's not skewed by outliers. So you actually have a better idea of where you fall in the pack, as opposed to, well, this guy got 100 and this person got a 0. Well, those are both going to skew the values. So then the last term we have here is mode. Hopefully everyone knows what the mode is. It's the most common value. So whatever number just repeats most frequently. Now let's talk about correlation. So there's positive and negative correlation. There's also no correlation, but let's look at positive and negative. And how is this defined? Does anybody know how this is defined? So this is defined on a running scale from -1 all the way to 1. So you're going through 0. So a positive integer shows what? A positive integer shows a positive correlation, meaning the two items being compared increase together. What does that mean? Well, hot weather and ice cream consumption. Let's think about that. The warmer the weather, in other words, the more the temperature increases, so too will the consumption of ice cream increase. That is a correlation, a positive correlation. How about on the other hand, let's talk about negative correlation. So negative correlation is going to be a negative integer. So it's going to be less than 0 on this running scale. And it shows as one increases, the other one decreases. So what's a great example for this? Kind of take the same example we just gave. If we increase cold weather, it'll be associated with decreased ice cream consumption. So the more cold we make the weather, in other words, the more we increase that integer, the more we will decrease the ice cream consumption integer. So to clarify, because this came up in the last episode, and this is a very, very cornerstone fundamental understanding in statistics, is that this is not causality. You cannot isolate confounding factors, right? That's what we talked about in the last episode, without conducting which type of study? A clinical trial. So finally, the closer the association coefficient integer is the whole number 1, the stronger the association and it will be. And the closer the value falls to 0, the weaker it'll be. Meaning, if you get 0.8, it'll be a very strong positive correlation, while negative 0.2 is a weak negative association. All right. The next term we're going to talk about is standard deviation from the mean. What is a standard deviation? And there's a whole equation for this. It's not necessary to know. But the standard deviation is very relevant to our bell curve graphs. The graph will be divided by standard deviations from the mean. That is how the graph is broken down. This shows variability of data around the mean. So if the standard deviation is very high, the data is very widespread from 50th percentile. And if it's low, that means your numbers are going to be more closely grouped together. From standard deviation, we get a rule. It's called the 68, 95, 99 rule. And this rule is the definition of standard deviation, where one standard deviation above and below the mean contains 68% of all data points. In other words, 68% of people fall into this group, meaning one above and one below the mean, or 50th percentile. Two standard deviations above and below the mean will therefore contain 95% of people. And 3 standard deviations above and below will contain 99% of people. The best way to get this concept is practice problems with the math. So try to get a feel for the concept, for what I just talked about, but really I recommend you apply it to problems while you're studying. Otherwise, the math gets a little confusing on if we're only looking at one standard deviation above the mean instead of one above and one below, then you have to split 68 and so on. So I recommend you just kind of get out there and do some practice problems. The next term we're going to talk about now is kind of taking the next step. So we've collected our data. We have the bell curve, we have the mean, median, and mode. And now the question is, what can we do with this? Or honestly, if I'm being more accurate, probably you're going to say, what am I setting out to do in the first place before you actually get these numbers? Ideally. What I mean is, we're talking here about the hypothesis of the entire scientific problem here, or study. So we're going to start off by talking about the null hypothesis. This is also known as H0. This is the base assumption of every study performed. What does that mean? It means that it states that nothing will happen, as in there will be no association or no significant result from the study. We will test if there's an association between, let's say, weather and ice cream. That's what we've been using until now, so let's roll with it. But the null hypothesis will state that there will not be an association between the temperature outside and ice cream consumption. The job of the study is to disprove that base assumption. So what does disproving that base assumption look like? Yeah, it looks like the alternative hypothesis, or H1. This is the researcher's goal of the study statement. There is an association present, or there is a statistically significant result here, and we're going to prove it with this study. And that is our alternative hypothesis. We're going to say there is something here, and we'll prove it. So how do we prove it? What value tells us, yeah, you proved it versus not so sure? That's going to be your p-value. So this is the most important value of any study, because all of the data you collected, all of the math you put it through, and all the different spreadsheets and all the different programs is going to spit out one little number called the p-value, and that's going to tell you, yeah, you did something here, or it's not significant. So what is a p-value? The p-value will, so to speak, translate to the probability that the test results will be at least as extreme as the ones observed during the trial. Meaning, it assumes the null hypothesis is true. So if you get a p-value less than, in general, 0.05, and we could talk about a little bit later where we get 0.05 from, but I'll give you just a hint, so to speak. 0.05 is the remainder from 0.95. In other words, we're 95% confident that the results in this study will be reproduced in at least as extreme result as we had here. Meaning, if we are that certain that these results are not a fluke, but in fact they will continue in any other study done, then the p-value is considered significant, and we are going to disprove the null hypothesis, because remember, the null hypothesis said that nothing's going to happen. But we're disproving the null hypothesis, and we are therefore introducing the alternative hypothesis of, hey, maybe it's this. Maybe there is an association. Maybe there is a significant result here. All right. That is the hypotheses and the p-value. The next subject here is error. There's two types of error commonly used. There's type 1 error, or alpha, type 2 error, or beta. We'll start with type 1 error, which is the wrongfully disproving the null and stating an association exists when it does not. In other words, that means it's a false positive result on a diagnostic test. So think when the disease is not present, but you get a positive result. And going back to our contingency tables, think of box B. Now we're going to talk about type 2 error, or beta. And this is the one that actually comes up a lot more often on tests. And there's a reason for that. Type 2 error, or beta, is stating that there is no significant result. In other words, failing to disprove the null hypothesis, when truthfully there is a significant association. In other words, this is a false negative. And can you tell me what box you think that might have been on our contingency table? It is box C. This one is more relevant to board exams. It is tested more often, mainly because the greater the beta error, the weaker the statistical power of the study. So ways to combat this is by increasing the sample size and precision of measurement. And both of these make for a more robust study with increased power, or in other words, increased ability to more accurately depict significance of an association. Those are your two types of error. If you were running out of headspace and you're like, I'm only going to remember one of these, focus on type 2 beta. So we keep talking now on and on about statistical significance. We have an idea of what that means, right? We understand that when a p-value on a study comes back less than 0.05, it's statistically significant, and we've done something here. We've disproven the null hypothesis, and maybe the alternative hypothesis is the answer. That's all good and fine. But what is clinical significance? And why is that more important often? Well, to understand that, let's understand the difference. We just talked about statistical significance. So clinical significance can mean, and here's an example, that the data may come back positive that a certain drug is associated with better health outcomes, but clinically the impact might just be irrelevant if it does not have any real benefit. I remember when I was doing my undergrad, I was taught this as an example of traffic patterns. You can do a whole long study showing that a certain route is statistically significantly faster than another route of commuting to work. But in reality, the time difference might only be 45 seconds or less. And in real life, you might not change the way that you commute and have been commuting for the last 3 years to save 45 seconds. You might just go with what's comfortable because you know it works and you've never had a problem with it before. So it might not be clinically significant, even though the p-value is less than 0.05 and is therefore statistically significant. All right. And then the last subject here, before we move on to the next, so to speak, topic, is going to be confidence intervals. So now we're going to tap back into what is that 0.05. So confidence intervals, I will say my confidence interval is pretty high that on board exams, they'll only be used in context of 95%. If you take a stats course, you'll see confidence intervals of any value, and there's whole equations to calculate what the confidence interval should be in order to show statistical significance, etc. But for boards, you just need to be familiar with 95%. So what we say 95% confidence interval, what that means is we are 95% confident that the range of numbers will contain the true population's mean. What does that mean? So for boards, we are 95% confident that X drug is associated with X benefit or outcome. This is used to reject our null hypothesis and prove our alternative hypothesis. So there are inherent exceptions when the confidence interval includes the number 0. So the interval would be, for example, negative 0.25 to 0.25. Then it would fail to reject the null and be statistically insignificant because it's neither here nor there. It's not, negatively associated, it's not positively associated, it crosses 0, it's just statistically insignificant. We failed to disprove the null. Another example of this, and this is one that I would bet that most of you will actually get this question on your board exams. If you have anything related to confidence intervals, I really think it'll be this. So another example is going back to that really pesky odds ratio that we've talked about in the previous 2 episodes. So in an odds ratio, they might give you a confidence interval, and the confidence interval may contain the number 1. So in this case, the range would be, let's say, 0.75 to 1.5. This shows there is no increased odds of the drug doing good versus bad, this versus that, since the value 1 or equivalent, because remember, this is a running range of values like we talked about before. It goes from -1 to +1, and you're crossing 0. Same idea. If you're crossing 1, then you're talking about a 0.75. So if one group in the odds ratio, if one group is exposed to something, and the odds of them having a bad outcome is 0.75 to the other one, you're going to say that they actually have less of a chance of getting the disease from that exposure versus another group. If they have 1.5, they're 1.5 times more likely to get disease from that exposure. But if your confidence interval that the population's mean is somewhere between 0.75 and 1.5, it's just as likely to be 1, it's just as likely to be equivalent, meaning they could have the same impact. It could be, if you smoke, you have equal chances of getting cancer as you do not getting cancer. Or you might have, 0.75, which is less chance, or you might have 1.5, which is 1.5 times the chance. So the point here is that if this is included in the ratio, we fail to reject the null hypothesis. The study has failed, And this is very relevant for odds ratios, and therefore what type of studies? Hopefully we all remember, case control studies. So if you ever have a question and it has a odds ratio sounding thing or a case control sounding study, and they show you a confidence interval and it includes the number 1, reject. Fail to reject the null, but reject it as the answer because it is wrong. It is not equivalent. The next subject we'll talk about now is the stats tests. These are the actual statistical tests you're going to do in everyday research. These are really good to know if you're involved in any extracurricular research projects. First one we'll talk about is the biggest one. It's a meta-analysis. What is a meta-analysis? So meta-analysis is a very precise method of testing statistical study results from numerous studies. So you essentially take the results from multiple studies, compare them, and make a very robust singular study. This is like gold star, top of the line. The next one we'll talk about is ANOVA. Does anybody know what ANOVA actually stands for? It's abbreviation. ANOVA is analysis of variance. ANOVA. This works by checking for significant differences between the mean of 3 or more distinct data sets. So if you have the mean of 3 different groups, for example, if you're involved in surgical review and you have 3 different surgeries and you're comparing the mean of all 3, you would want to use an ANOVA to see if anything has any significance to each other. One's better than the other, or if none of them are better than the others. This is, however, is very limited in the fact that it does not say which data sets are different. So when you do an ANOVA, it might say like, hey, yeah, at least 2 of these groups are different from each other. Could be 2, could be 3, could be group A is different than group B, group A is different than group C, or any other combination thereof, but it doesn't tell you which one. It just tells you there is a difference here, or there is no difference between the 3. So as far as boards, you don't necessarily need to know this, but I'm putting this in here if you are doing a stats project. There are follow-up tests that can be performed to single out. So now that you know that there are differences, to single out which groups have differences, it's called a Tukey test. You could look that one up if you're kind of stumped on a group project, but it is not relevant for boards. The next test we'll talk about is the p-test. This is the ANOVA, but only for 2 groups. This is the significant difference between means of only 2 groups. So, the surgical cases only has 2 approaches, and you're just comparing those 2 directly. The next one we'll talk about is a paired t-test. We just talked about the t-test. This is a paired, as in grouped t-test. What is a paired t-test? It is used to evaluate the difference between 2 means from a paired set. For example, the average blood pressure of Joe before intervention, and then his average after intervention. So it's before and after test of the mean groups. So you're looking at, patients before and after intervention, and you're actually using their mean before and after to compare. So you're still comparing the means of only 2 groups, but it's the same person as opposed to 2 totally separate things. So the t-test would look again at like 2 different surgical approaches. The paired t-test might look at a patient's survey responses or blood pressure averages from before and after intervention. The next one we'll talk about is the chi-squared. Chi-squared test is the same idea. So it's a significant difference between 2 or more proportions for categorical data. So it's the same idea as the t-test. However, it's for categorical data as opposed to quantitative data. So everything until now has been mean analysis. For example, the average blood pressure was, 120/80. That's mean, that's an average. Categorical data is not numerical. So it is either something that's present or absent. For example, the proportion of yellow versus red houses on a block. So it could still be a number, it could be a proportion, but it's not the average. It's just, there's this many red houses versus this many yellow houses. Or to stick with blood pressure, the proportion present of hypertension in different age groups. So hypertension is present would equal a 1, and not present would equal a 0. And your study would consist of 1s and 0s, and you're going to compare the 2. And you get discrete, based on the groups are based on discrete ages. You're gonna group them and bin them together and use a chi-squared. Essentially, if you ever see something that isn't an average, it's just categorical data, think chi-squared. All right, last thing we're going to talk about is the types of prevention. So the types of prevention are primary, secondary, tertiary, and quaternary. What is primary prevention? Primary prevention are the measures to avoid incidents in the first place. And this is episode 3, but I'm going to ask you again, what is incidence? Incidence is the onset or diagnosis of new disease in a at-risk individual from the population. So, for example, primary prevention. An HPV vaccine, which would prevent contraction of HPV to begin with, would be primary prevention, because ideally we give the HPV vaccine and that person doesn't contract HPV. Obviously, we're talking about the strains the HPV vaccine prevents. Secondary prevention, what is that? This is early disease identification. In other words, subclinical identification. Well, what does that sound like? That sounds like screening, right? These are screening tools. You're not going to do a screening test if someone has symptoms. You're going to do a diagnostic test. So secondary is not diagnostic, it is screening. For example here, and we'll stick with HPV, routine pap smears to identify disease before the symptoms of cancer would be present. So again, secondary screening, SS, secondary screening. The next one is tertiary prevention. What is tertiary prevention? Tertiary is going to be the next logical step here. It's methods to decrease morbidity and mortality, and they can be medical or surgical interventions. So doing a LEAP procedure, doing anything like that, now we know it's here. We're trying to reduce morbidity and mortality. That is tertiary prevention. And finally, quaternary prevention is going to be decreasing any potential harm from the treatment of said disease. In other words, this will be research and implementation of efforts to make the HPV vaccine safer. So we're actually, quaternary is kind of like on the side while we're doing everything else. We're going to try to make the treatment for said disease or the prevention of said disease safer. So whether it's medication, surgery, or the prevention stage, just making them safer, more readily available to the public. That is quaternary prevention. So my best advice here, at minimum, be passively familiar with the concepts that we've talked about in all 3 episodes. Ideally, have the basic equations memorized based on only the contingency tables. Just practice writing them out. Like I said, try to Google a form or a page that just has all of them written out. I know I was able to find one, and just practice out all of your practice tests, or when you sit down to do practice problems, especially stats ones, try to write them out by memory just so you're forced recall, and hopefully that'll get you able, over the hump of that concern with equations and contingency tables. And go from there. The rest of these are all really just concepts you could be familiar with. There are some other equations, especially in this last one, where it's good to be familiar with, like what happens to mean, median, and mode as the bell curve changes. It's very well illustrated in first aid and plenty of other online resources. And that's what I have for you. Whoever's still here listening after 3 of these episodes, thank you for listening, allowing me to help your board's journey. I really appreciate this opportunity and hope you all do really well. Good luck. And remember, you got this. If in doubt, my best advice would be practice questions, practice questions, practice questions. Thank you for listening. If you found this episode helpful, please subscribe to our podcast. If you have any questions, comments, concerns, visit our website at spoonfulofsugar.org and post them onto the link in this episode. Good luck with study, and remember, if you ever have an SOS moment while studying. Spoonful of sugar was always here to help the medicine go down.